Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Georgina.
Hello.
Welcome.
Hello. I'm a DPhil student here at Oxford doing my first year of my PhD.
Hooray! Thanks for joining the Maths Club today, Georgina. Georgina's made some slides to tell us about rooting around, finding roots of polynomials with small terms. And if you want to join in live, you could let us know in chat that you're here. Like, for example, Aaron, who's just joined chat to say hello. Hello, Aaron. Um, that live chat that's happening underneath there is not YouTube chat, it's happening on Slido at slido.com/OOMC, which has the additional feature that you can be anonymous, like these two people, or possibly one and the same anonymous person who've joined just to say hello at the same time as each other. Possibly that's one person. And here we go. Right, good. Okay, so we're going to do some polynomial stuff. That's the plan. But first, I always want to know how their day is going. So hi to Liz and Joe in chat. If you've joined us before, you know we do a 5-star scale for how is your day going on a scale from 1 to 5. Oh, okay. Georgina, how's your day going on a scale from 1 to 5?
I've actually had a really good day today. I've had a lot of code working that was not working previously, so feeling
Ooh,
productive.
are you allowed to say what your code's doing? What?
My code is, I'll talk about this when I mention my research at the end, but my code is trying to model how ions move in solution, so it's kind of like a chemistry problem.
Oh,
And I'm really struggling to make my code run with like keeping all my parameters as like variables that I could sub in later. And then I figured out how to deal with that today. So my code runs in a reasonable amount of time now.
nice. Always the dream. Code that works and also runs in a reasonable time. Good.
Exactly.
Right, chat's not having a great day. At least two
Oh
people have
no.
ticked the 1-star button. I'm always looking out for people who vote 1 star because they're having the worst possible day on that scale. Um, and our only hope is that either their day gets slightly better as a result of polynomials, or possibly that it gets slightly worse but wraps round again to five
Yes.
stars. Possibly the left and right edges are identified. We can find out. Not that my intention is to make anybody's day even epsilon worse than it currently is. Right. Okay. Good. There's also lots of people having a nice day. It is currently sunny in Oxford, so I am having a nice day. How is chat going over here? We've got Mary and we've got Anonymous and Ketame have joined chat as well. Good. Right. Okay. And Hamish is here despite partial fractions. I am also partial to some fractions, so you know, good times. Right, okay, that's chat. Chat's here, Georgina's here. I should shut up and let you talk about polynomials. Over to you, Georgina.
Amazing. Thank you, James. If we could jump to our first slide. The goal of today is to discuss how we can use some like interesting techniques or interesting analysis to look at how the roots of simple polynomials change when some terms in the equations get small. We'll see what that means in a second, but basically we're going to be looking at functions that you hopefully know and love, like some quadratics, some cubics, and seeing how we can make approximations or like analyze the behavior of the roots of these functions. So the roots being the x-intercepts or like the zeros, depending on what terminology you're used to. The important thing to note is that like these examples are relatively simple. When we're looking at quadratics, you might be like, hey, I could just use the quadratic theorem. Yes, you can. But the analysis we're going to do gives you some really interesting insights that you might not get from just looking at a square root in the quadratic theorem. Like it gives you some intuition for how the root is going to behave. And the techniques we're using all generalize in research math to like much, much harder problems. So we're looking at like a nice simple thing that you could do just with the quadratic theorem, but we're doing it for a reason. And I think you'll hopefully find it cool. So the first thing we wanted to do is just to get some basic context, make sure we're all on the same page. Let's look at the roots of a simple quadratic. So if we look at x squared minus 1, and we want to find the roots, so we're going to solve equal to 0, we can solve this very easily. So we can just take a difference of squares. If next that will, and then we can solve this to get x equals 1 and x equals -1. Hopefully everyone is comfortable with this. This should be stuff you've seen. Yeah? Amazing. So the question that we're interested in if we go to the next slide, is how do those roots change? So our +1 and -1, if we add a small term into the equation. So if we turn our equation to look like this. So what we've done here is we've taken x squared minus 1. We still have that. And then we've added in this new term in the middle called epsilon x. And now epsilon is kind of a constant we often use in math that just means a small thing. In the same way where you're like, hey, I need a spatial variable, I'll probably choose x, or I need a vertical variable, I'll probably choose y. Whenever you need a small thing in math, people often choose epsilon or epsilon, depending on what your accent will give you. So yeah, whenever you see that funky E thing, it just means this is a small number. But we can also treat it as a variable. So we can move epsilon around a bit. So we can say it's 0.1 or it's 0.001, for example. I've written this little notation here where I've said 0 is less than epsilon. So that means epsilon is a positive number. It's not negative 0.1. It's going to be 0.1. That will just make some of our math easier later on if we know it's always positive. And then I've done this double arrows less than 1, which just means that it's really less than 1. So epsilon is not 0.9, it's going to be 0.003 or something like that in practice.
I love this notation. It's like putting 2 exclamation marks to indicate that something's very surprising. It's much less than 1. So this is a really small number.
And yeah, this is the official legit math notation for it, which I love. The important thing, or the cool thing we'll find is that, and we'll discuss this potentially later in the session, is that we need to start with the assumption for everything we're going to do to work that it's very, very less than 1, but we'll see that we can be a bit flexible with that. And maybe what counts as small is not actually that small, which is a kind of cool thing about this theory. So if we just go next, we'll see our question is now, we've added in this little term. We've added in an epsilon x. And we want to know how that changes the location of the roots. So we know the roots started at x equals 1 and x equals -1. Now that I've added this little bit into our equation, what has happened to those roots? How have they moved to the right? Have they moved to the left? How much have they moved to the right or left? That's what we're kind of want to figure out. So if we go to our first Desmos, James,
I should say, Georgina, for people watching at home who love Desmoses and have seen occasionally some Desmoses, mild spoiler, Georgina has prepared 7 Desmos charts for this, which I'm so excited by. Okay, so number 1, this one.
I often joke that I think I did my entire undergrad degree through Desmos. I'm like, if I can do something visually, I will. But yeah, so what we have here is in red, we have our plot of our original function, x squared minus 1. And then in blue dash, we have our plot with this small term added. So with the plus epsilon x in the middle. And so you can see, we want to observe kind of what's happened here. And we can see that we've shifted our function and it's gone a bit to the left. So I've seen some people in the chat say they decrease a little bit or they move to the left. Yes, yep, that's correct. So that's a good intuition. James, if you make epsilon quite big for me.
Oh, quite big. So it's currently 1.12, which I notice is not much less than 1, but again, if I go quite large.
Yeah,
okay, well, they're over here now.
Yeah, the one thing I want you to notice here is that when epsilon's really big, these look like 2 very different quadratics. These are not the same thing. We're not going to be able to particularly use information from the first quadratic to get information from the second quadratic.
Sure.
But now, James, if you make epsilon pretty small, so maybe 0.1, 0.2, something like that. And yeah, let's just zoom in a little bit to our main quadratic. We can see these are pretty similar, right? They look basically the same, just with a slight shift to the left. So that gives us a good intuition that we'll be able to use information about this original quadratic to try and guess what the roots are of this new quadratic. Does that make sense?
Yeah, I like that. I think some people in chat voted for left. And they're possibly now going to go away and think about, I think people watching know loads of stuff about quadratics in particular. It's a good starting point. Maybe they're thinking about completing the square. Maybe they're thinking about the quadratic formula or the quadratic theorem
Yeah.
for writing down the roots. But is there a way to guess that they were going to go left from the fact that we're adding? I don't know if that's obvious or not.
Probably is. The I didn't think about that off the top of my head, but like how to guess it was left. Maybe someone in the chat can tell us how they all knew that it was left.
Yeah, there's a left-right vote. While they're telling us, and I'll give a few of them a chance to tell us, why have the roots gone left? And it's like both of them have gone left. It's broken the
Yes.
symmetry. Like before, it was an even function, and now
Yeah, it's definitely not a function anymore.
it's not an even function anymore. There's also a question in chat about EPQs, which is an essay that some people do in school. Did you do one of these?
No, I
Okay.
grew up in Australia, so
Okay. Not a thing in Australia. They're a thing in some
no,
UK
unfortunately.
schools. I didn't do one of them either. And the question in chat was whether Oxford used them for admissions, and the answer is just sorry, no, we don't use them as part of our offer process. But we often think that if you've got a chance to do an EPQ, then it's a bit like Maths Club. It's a way to maybe go and find out a bit of maths, write about it, and tell other people about it as well. That's probably helpful when
Is
you're
it
thinking.
kind of like a report, like project independent investigation kind of thing?
Yeah. So you do some sort of investigation. Possibly you, I don't know, read a lot of Wikipedia pages, or maybe you. One of the reasons we do Maths Club actually is that maybe people want to find a topic from Maths Club and then go and read the further reading notes. People watching at home, we put further reading notes on the Maths Club website. Link in YouTube description to the Maths Club homepage, where we put further reading notes up the day afterwards. Right, people are thinking about transformations of graphs. Ria, who said it was their first time here, said yes about translating f of x minus, and they've got x minus 9, but they're thinking about translations, which is, I guess, related to completing the square.
That makes sense.
Aaron's got a translation argument, and then there's lots of people saying there's a positive value up to the change. I suppose epsilon is a positive
Yeah.
number. You've got to think a little bit about
So yeah.
x.
So yeah, if you're solving equal to 0, it's whatever it was before plus a positive thing has to equal 0. So now that thing has to be slightly more negative to like x squared minus 1 has to be more negative than it was before.
Yeah. Okay. Good intuition, chat. I like it. Good arguments. Georgina,
Awesome.
yeah, I think you've got a technique for making this rigorous and precise, which is
Yes, I do. Let's just jump to our slides again, to the slides with the table. One thing I want us to kind of do to get a feel for this, so it's the next page, is if, and just next again.
Yeah, sorry.
Oh yeah, so this is just my observations firstly of what we saw. So we saw that it was a quadratic shape, and the root shifted left, and they kind of moved at similar speeds. So they didn't like shift particularly asymmetrically. They both moved kind of a similar amount when epsilon was small. But then if epsilon became big, then the quadratic just looked very different. But what I'm interested in here is seeing if we can kind of quantify that, the fact that they both moved to the left a little bit. So if we go to the next slide, what I've done here is made a table of what the epsilon value was and what the roots on the right and left became once I made that change. So I want to know if anyone in the chat can come up with like a approximate kind of rough relationship between what the epsilon value is and how the roots moved.
Sure. So we're looking for some sort of simple approximate equation to describe what's going on here. I'll try and provoke chat into doing better than me. So mine would be like, these ones are all about -1 on the left, the ones on the right are all about 1, but you want me to look closer than that, right?
Yeah. And so that's a great starting point. And then let's think about how the value relates to the epsilon value. So we've gone from -1 to about -1.05 when epsilon is 0.1. How are those things related?
Right. We're going to give chat a second to let us know and put things in chat. Because lots of people are typing at the same time as each other, I'll state my standard thing, but if you're typing and someone else posts something in chat, carry on typing, press enter. I'd like to hear from several people if I can. Yes, good.
I think some people getting some good things.
Yeah, there's some ideas. It's always the I like waiting as well because it's also like the length of message is also
Yeah,
if I wait long enough, someone's probably still typing an essay about
it says come through.
one of those EPQs, right? For it's gone quadratic has gone to the left or something. Yeah, so there's a theme to chat messages, I would say. Adding or maybe subtracting or something to do with epsilon divided by 2.
Yeah, and that's the key thing I really wanted to get across here. So when epsilon is 0.1, half of that is 0.5. And so we get to like minus 1.0.5 or 0.95 approximately. Does that, hopefully that kind of makes sense. Just take a second to look in that and go like, okay, if it's 0.3, half of that is 0.15. We're getting to negative 1.16. That's about negative 1.15. 0.86 is about 1 minus 0.15. 0.85. It's about the same thing. So hopefully that relationship kind of makes sense that it's aligning with this epsilon value. We're kind of moving almost like in a linear way with this epsilon value. So it's proportional to epsilon. But it's not exact, right? Like it's not negative 1.05, it's negative 1.051 decimals going on. So this is not a perfect relationship, and we're going to need some correction terms to make this relationship more exact. And so if you just go next twice.
Yes, sure. Sorry, yes. So we could, I guess, these numbers that you've put in the table, they've come from like looking at the
Yes.
Desmos really closely or something. So we could,
Yes.
I guess we could go and zoom in and find out what those are and play the game with chat again. But you've got a better method that doesn't involve numerics. Let's go. Sorry, yes.
Exactly. And so we saw that the first relationship was linearly dependent on epsilon. So it was like a linear equation, just an epsilon to the power of 1. And a good idea that we can use to figure out what those correction terms would potentially need to be to get like the next set of decimal places correct is to look at like epsilon squared terms. So it's still proportional to epsilon, but now it has an epsilon squared factor. So we're like if it was 0.1 was epsilon, we'd be looking at a 0.01 correction. And we keep working with that. And you could technically make this an infinite series. But the nice thing about asymptotics is that it generally gets really accurate really quickly. So we'll find that we get a good approximation to the roots if we only go up to epsilon squared. But you could go up to epsilon cubed, epsilon to the 4, epsilon to the 5 to get better approximations.
Right. This is like a Taylor series or something. If epsilon is a small number like 0.1, then who cares about epsilon cubed?
Exactly.
Me,
If
me
you
a
know
little
what a
bit.
Taylor series is, then this is a Taylor series.
Oh yes,
If you
right.
do not, which is likely, then do not worry about it.
Yes, sorry. That was the sort of comment that I do sometimes. That is useful if you already knew it, and not useful if it doesn't. Right. Yeah. Sorry.
That's all good. Basically, what James is hinting at is there's a lot of calculus under the hood here that we're just not going to worry about.
That's me. Do you want your core idea slide?
Yes, please. So the reason, and yeah, you can put up a few of the dot points here.
Okay.
The cool thing is that what we're going to do is take this guess for x, and we're basically going to kind of do like a guess and check method where we're going to say, hey, if x has this form where it's some answer a, like the answer as a constant, plus a correction that's proportional to epsilon, plus another correction that's proportional to epsilon squared, let's sub that into our original equation, assuming it's true, and see what the coefficients A, B, and C have to be to make that correct. It's kind of the core idea we're going to work with. But each level of adding in an epsilon is another level of a correction. So that means we can't have our answer rely at like, so let's say A is kind of level 1, B is level 2, C is level 3. We can't have our answer at level 3 depending on the result for level 4 because we don't need to make that correction. We can stop at level 3. So similarly, our equations for B can't depend on our equations for C. They can depend on our equations for A, so we can depend on the level above in our like series, but they can't depend on the level below. And what that means is that when we substitute this into the equation, we'll see that we get equations where we'll have a bunch of constant terms, and then we'll have a bunch of epsilon times stuff, and then we'll have some epsilon squared times stuff. And because we know that the corrections can't depend on the lower orders, we could start by solving all the constants. And that has to satisfy the equation that they are equal to 0. And then we can look at the epsilon terms, or the things that are multiplied by epsilon, and solve those equal to 0. And we can then solve the next level below that. So we can kind of work through it progressively with each level only depending on the stuff that came before it.
That's the big picture. Sorry to interrupt.
Yeah.
Something I like about chat is they let me know if they if they're struggling. So this is the big picture. We are going to walk through it step by step. So if they haven't followed it from this, that is fine and expected. But the kind of super big picture, if like me, you just want the vaguest of ideas, is to solve this thing on the left. You could go and get the quadratic formula, but we're going to try something different. We're going to try one weird trick, which is to try writing it as a number plus a little correction with just a little bit of epsilon. We just saw that the roots were like minus a half epsilon plus, or maybe that's not quite right. Maybe a bit of epsilon squared, and so on and so on and so on. And we're going to do that until we get bored. But we're going to try and make sure that we choose the numbers A and B and C so that this actually makes sense in the equation.
So to make that point clear, when we'll work through this example in a second, and we found that our results were like 1 minus epsilon on 2. So we're going to expect that A is 1 and B is negative a half, for example. So that's how this kind of series forms links in. The important thing is basically, like, another way you can think about it that might help in a second is that we're going to be matching orders of epsilon. So I one comment I realized I made that if people were following along, which it's fine if you weren't, is I was like, oh, we'll solve each thing equal to 0. And that might have been a bit confusing, or it's like, why that? Basically, we're kind of, you can think about it as like equating coefficients on each side, and the fact that there's no epsilons on the right-hand side of this equation means that it's like 0 plus epsilon times 0 plus epsilon squared times 0. And so then that will all be zeros. That will make more sense later.
Okay, we're gonna jump into the example, I think, but just an English language thing, which we're saying corrections, which so English language. So this is a correction is something you do if you were wrong. Then you have a correction to try and improve your answer. If you're watching at home and you've never been wrong about anything, then I understand that might be a new word that you're meeting. But it's a thing in maths as well, where you have these kind of approximations, and we're going to try and see increasingly good approximations. Like how 1 is not a great answer to what are the numbers in this table. Saying 1 is not a great answer. Saying 1 minus epsilon over 2 is a better answer. Right, good. Sorry to interrupt.
Yeah, so an alternative word for correction could be an improvement.
Yes, chat's also got a tiny adjustment because the higher the power of epsilon, the smaller the value is. Okay. Algebra time.
Exactly.
Algebra time?
Yeah. So let's give this a go. It will hopefully make some more sense when you see it. So we're starting with our original equation, which is x squared plus epsilon x minus 1 equals 0. And we have our guess for what x should be. So we're going to say x is a plus epsilon b plus epsilon squared c, where a, b, and c are constants. So they're just going to be a number at some point. So let's start by subbing that into the equation. So we can use our squaring laws. Epsilon multiplies nicely out in the bracket. We have done the math for you, so you don't have to worry about squaring things out. And the nice thing, as I said before, about the fact that we only to get an answer to epsilon squared, we don't care about any of the higher order corrections. So anything that from this expansion result with an epsilon cubed or epsilon to the 4 or any other higher power, we can just ignore. We pretend it doesn't exist. Those are all hidden in the little dot dot dots in the equation, basically. And so if we do that, you can see our first term that James was just underlining will get us an a squared from that big square bracket. And then we still have a -1 over there. But everything else is going to have some factor of epsilon in it.
Oh,
This
there's
is
loads
literally
going
just
on.
expanding brackets. It looks kind of complicated, but it is just expanding brackets.
It's really important, isn't it, that you're ignoring the things that have epsilon cubed in. So if I was going to multiply
Yeah.
out this infinitely long thing, I'd get infinitely many terms, but you're ignoring loads of them. My goodness.
Exactly. Yeah. We just don't care about those. Shove them into the dot dot dot. They don't matter. And so we get this equation, and we're going to solve this equation at each level of epsilon. So if we look at it, you can see we have these terms out the front, a squared -1, that have no epsilon associated with them. They're just chilling. And then we have this next set of terms that's epsilon times a plus 2ab. So that's kind of, we would use a term like our first order equation. And then we have our second order equation, which is this b plus b squared plus 2ac. So these are the things with the epsilon squared. And we're basically going to work through solving each of these things equal to 0, because we're solving for roots. So we need our equation equal to 0. But we're just going to solve them as each individual bit equals 0.
Yeah, good. Okay. So there's a lot of work in squaring, but then once you've got there, you get these. The equations are not too bad. We're going to do them one at a time, aren't we? Oh yes, here we go.
Yeah, beautiful. So our first one, our equation that has no epsilons with it, so it has an epsilon to the power of 0, which is 1 kind of coefficient. We can solve a squared -1 equals 0, and that gets us a equals plus or minus 1. Now, the really nice thing, if you just hit next. So we found if there was no epsilons, if epsilon equals 0, we got x equals 1 and x equals -1, and that aligns with our result here.
We're back at slide 1 when there weren't any epsilons. It was just the quadratic x squared -1. If epsilon is 0, then nothing's happened. But
exactly. So with no epsilon corrections, that's our result. Now we'll use we're going to just consider the case where a equals 1. So ignore the -1 solution for the moment. And we could sub in that a equals 1 into our next equation, which was a plus 2ab equals 0. And that will just give us 1 plus 2b equals 0, which we can easily rearrange. Also be happy for us, because we know we said that we were expecting a to be 1 and b to be -0.5 from our first observation that the root was behaving like 1 minus epsilon on 2.
That's the thing that people in chat said.
I'll give everyone a second.
Just by looking at the numbers, that's the thing that people in chat said, -0.5. Now proved with maths as the correct answer. But you've got one more on this slide, haven't you?
Exactly. So now let's figure out that next kind of level of correction. So we'll look at the epsilon squared, and we can sub in our a term and our b term. So a equals 1, b equals -0.5 into this equation, and we'll get that c equals 1 on 8.
I don't think I'd have been able to guess.
So then, which I wouldn't have guessed either. If we then put those back into our series, we end up with this kind of form. So subbing in those values for a, b, and c, we can get that x1 is equal to 1 minus epsilon on 2. That's what we already had. And then we know that the next level of correction is epsilon squared on 8. Now, these equations are the same for both solutions for A. So I'd be interested to know if you guys could work through quickly what the result would be if A equals -1.
Right, so this is
and a little spoiler alert, you can use the fact that we guessed that B was -0.5 as well for the second case. So you only actually need to work out what C is in the case where A is -1 and B is -1/2.
Oh, you see, it's like a kind of choose your own adventure where the choice you make up here about which route you're talking about, are you talking about the 1 route or the -1 route, that follows through, doesn't it? Because now if you choose -1, you'll get A's in here, and then an A down here will have a minus sign in it. And oh my goodness,
Exactly.
right,
That's
okay,
what we were saying, that it's like your result does depend on the higher, like the levels before, but it doesn't depend on the levels after of the corrections. But yeah, you have to know your starting bit of the series to keep going.
There is a prediction in chat that the next term they've spotted a meta pattern, which is when they've spotted a pattern in the patterns. They have a guess about what happens after this, which I'm impressed by, and I think they might actually be correct. But maybe we'll leave it as homework. I think I still get B as -1/2 in this case, because the A I can divide by A on both sides anyway. But then down here it becomes different because I have the same value of B, but I have the opposite value of A. So
yes, exactly. So we're just changing that +2C to a -2C. Yeah. And yeah, James is correct. We get C equals -1/8. Hopefully some people in the chat got that on their scratch paper at home. And so if we jump to the next slide, and again, we'll get the full table. We can see that these are the two solutions we found. So our approximations were that x1 is equal to 1 minus epsilon/2 plus epsilon squared on 8. And the second one was -1 minus epsilon/2 epsilon minus epsilon squared over 8. So that's what we just calculated correctly, or like in full and rigorously. And now we can see how the values that are the actual numerical results for the root, so just pulling the results out of Desmos, compare with our approximation. I don't know why something's beeping at me. Okay. Yeah, and we can see, I think these are pretty good.
It's pretty good. We had the kind of idea that it was 0.95, 0.9, 0.85, but this has now corrected that to, I think we got another decimal place on here. I think there's a 5, there's a 1, there's a 9, which I guess an extra decimal place makes sense if epsilon is 0.1, if epsilon is 0.1, then this is almost exactly like calculating one decimal place at a time. You do a calculation to find out how many 0.1s you have in your number, how many 0.01s, how many 0.001s, and so on and so on and so on. You get the kind of place value thing going on. Should we address the elephant in the room, which is the binomial expansion and the quadratic formula?
I
can say something.
Yes, please do. Because what I was going to say involves Taylor series.
Yes, so some people in chat have spotted that they can solve this expression using the quadratic formula, and then possibly you could take that solution and expand it with the binomial expansion to get an expansion. And also Aaron in chat has spotted the opposite, that you could take this expansion, you could recognize the binomial, and you could squash it back down perhaps to turn it into a square root. I think that's all true.
Yes, and that makes a lot of sense because one of the like kind of forms of the binomial expansion of a square, or like if you have learned about like more complicated binomial expansions where you can do like a power expansion where you have like a fractional power instead of a whole number power, that in technical math terms is the same thing as a Taylor series, which is the same thing as what this is under the hood. So yes, they are extremely related concepts. So very good.
That's a good reminder for me that I'm not sure when people learn binomial expansion with a power of 1/2 on it. So if you haven't seen that at home, don't worry, I'm going to put something in the further reading notes so that
I think it might be a uni thing.
If you check the page, if you check the web page at some point tomorrow, I'll put some further reading notes up for how to expand the quadratic formula. But the point I want to make is, well, you've done very well with the quadratics there. Let's see how well you do with the rest of the polynomials in today's session. The quadratic formula is great, but we can use this technique on polynomials that we have no chance of solving.
Exactly.
Right.
Let's go to our next slide.
Yeah.
So the interesting thing about this method is that we're basically using the solutions for an easy to solve problem, just x squared minus 1. We knew the solutions were 1 and minus 1. And we were able to use that knowledge, that that's what the first two terms in our kind of series expansion should be, to find a good approximation to a harder shifted problem. So this problem that was shifted by this small term. The fancy technical word for when we've like shifted a problem slightly is called a perturbation. The way I like to think about that in my head is that to be perturbed is a word for like to be annoyed in English. And I always imagine like if you had a little sibling like poking you just a little bit, you would be annoyed. So if you've given like a small little push to something, you've perturbed it.
Right. You've given it a little nudge. Lovely.
Yeah,
Okay.
you just perturbed it a little bit. Um, and so the whole class of stuff we're doing here is called perturbation theory. So it's mathematical theories about how things change when you shift them a little bit and using easy problems that you know how to solve plus perturbation theory to get the answer to the harder shifted problem. So let's jump into something a bit more interesting, as James was just saying, which is studying something that's a bit harder than just a quadratic moving around like 1 and -1. So let's look at a general polynomial. So here we have a cubic and it has unknown coefficients A, B, C, and D. That could be general numbers. And we're going to look at when these roots have kind of an interesting behavior. So not just the roots kind of slightly moving back and forth, but when something funky happens. So James, if you could jump to the Desmos now, example 2.
Yeah, getting it on screen.
And what I would love you to do is hit the little like play button on each of the
Oh, right,
coefficients.
okay. Oh, let's see if I
So
can
what we're going to
manipulate
be
this.
doing here is randomly generating the coefficients and seeing how this cubic kind of moves organically. And while we watch this, I want you all to look out for when a funky behavior happens, which we'll see in a second. And I want you to try and figure out which parameter that behavior is corresponding to. So one of these parameters is going to get small and something funky is going to happen.
All 4 sliders going. My computer's trying its hardest. Oh, so there's something really weird there just for a second.
Yeah, so that was the funky thing.
Which one
Let's
was it?
watch it again.
So there's one of the parameters going small. So not D, that one is controlling the y-intercept. Here comes C going in towards 0. And that one's controlling something complicated. We're going to look at the A and B sliders as well. Oh, this is really... I'm sorry for the frame
they're
rate.
quite close together.
They are quite close together. I can fix that.
Yeah, maybe you might need to offset one of them.
Let's try just running B for a second, see if that makes my computer happy. There's something almost no effect on the polynomial. It hits 0 and hardly care. I think it might have stopped. I might have crashed Desmos.
It's still running to me. Oh, maybe it's not.
Maybe not. Right. Is this happy? Oh, there we go. Okay, I can move one at a time, maybe manually. So if you make A really small to 0, something's changed.
Yeah. And if you could go through and just kind of like vary A between like 0.1 and 0. So if you just like change the right hand of your slider, if you click on the like right bit of the slider value for A.
Oh, right, okay, hang on. Yeah, I can put this in as like a mouse.
Yeah, just make that it's like 0.1.
Okay,
and
so if
see.
I flap this around, it changes kind of quite dramatically on the left.
Yeah. And so if you just hold it above 0, but like very close to 0, we can see that it's doing this very funky thing where when it is exactly 0, then we've lost our x cubed term because we have 0 times x cubed. And so we just have a quadratic. But if we have a little bit of A, we still have to technically be a cubic. So we have to have the full going to negative infinity shape, but it's only like just a cubic So we need to look like a quadratic for most of it. And so we're ending up with this very kind of funky behavior where our little negative branch is trying to swing out.
Yeah. So there's a question in chat about why only the negative side changes visibly. I think actually the positive side is changing too, but it's very positive in both cases. So it's kind of changing from very high to very high to very, very high. I think that's hard to see. I need to close some tabs.
Yes.
Cover for me while I try and fix my computer. It's giving me all sorts of, it's not happy about this.
Yeah, we've asked it to do too many polynomials.
I'm not even sure I can close this. Oh, right, there we go.
Beautiful. So the things that we saw were that if we had this a being small, our function wanted to behave like a quadratic, but it kind of couldn't. So it had to do this thing of like sending that negative branch out really, really far. And so we'll look at this behavior, but we also saw, importantly, that if B, C, or D became close to 0, everything kind of like hung around the same area. It didn't do any particularly dramatic changes. It was only if that leading highest power term had the coefficient going to 0 that we noticed things that were funky. So now let's go back to quadratics.
Right.
Fun, safe home territory.
Yes. So here's a quadratic. And you got the question, how many roots does this quadratic have normally?
Yeah, so consider this is a quadratic that has the maximum number of roots a quadratic should have. So how many roots is that? How many do we expect?
Now I find out if I've crashed chat as well. I think it's all happening. Trying to desperately close tabs so that I can give my computer, poor little computer. Right, good. Yes. So the observation is like the change in the degree of the polynomial. That was the thing. People said it was turning into a quadratic, right? So
yes.
Is it a cubic? Is it a quadratic? Yeah. How many roots? We're down a degree for this example because it's only a quadratic at best, isn't it?
Yeah, exactly. So if epsilon was 3 here, how many roots would you expect this quadratic to have?
Thank you, Luke, Star, Igar, and Joe, who have joined in chat with the number 2.
Beautiful. 2 is the number I was looking for. No trick questions here. But then we know that if we set epsilon equal to 0, this function becomes x minus 1, right? Like if I just sub in epsilon equals 0. So we need to have our quadratic go from looking like epsilon x squared plus x minus 1, so a thing with 2 roots, to something that looks like it only has 1 root. And so if we just go to our next question, if we're going from epsilon x squared plus x minus 1, so our lovely little quadratic, and we're going to send epsilon to 0. So this means that we're going to, basically on our little decimal slider, where we see epsilon arrow 0, that means we're going to pull our epsilon to the 0 side of the decimal slider. What's going to happen to that root out on the negative side? What's it going to do?
Right, so there's a fundamental difference between epsilon being 0 when it's someone in chat. Where does that say? As epsilon gets small, this starts to resemble a line. Of course, if epsilon is not 0, it's still not a line. It's a quadratic, but happens to have a very small number in front of x squared.
Yeah, I've seen some people say like one of the roots has to tend to infinity, and I've probably spoiled that a bit with the first line of the slide. But that is exactly right. And I think I saw someone else saying like the negative root will have to like go out really far.
There's another guess that they get closer together, which that would be exciting. If the 2 roots secretly became 1 root, that would be fun as well.
Yes, and there are systems where things like that can happen, not unfortunately in this one. James, if you pull up another Desmos plot, this would be example 3.
Let's see
We
if
can
my
have a look at this.
computer can do it. Is it a big Desmos or a normal sized one? Oh, it's fine.
This
It's
is
just going to let me change the
this is the
title.
baby one.
Baby one, right?
Yeah.
Okay. Here's the graph.
So yeah, our graph, and then we're just going to make epsilon small.
It's cutting off Georgina's audio as it does this. So as I make epsilon small, one of those roots is staying still near 0, and the other one has gone off the screen to the left. It's disappearing off to -50, -60, where's it gone? -100.
Go ahead.
Yes, one of the side effects of running the Desmos seems to be that my Zoom call is deteriorating as well. Good. Yes, with one side stretch out. There we go. Stretch out like how the cubic stretched a bit before becoming a quadratic. Yes, exactly that, Ria. Thank you. It's stretching out wider and wider until, I mean, that looks a bit like a straight line, but in fact, if I zoom all the way out, it is in fact. Oh no, I've set it to 0. It is now a straight line.
I think you have it as actual 0 there.
I have it actual 0, yeah. Good point.
It looks so much like a straight line that it is one.
Yes. There we go. If I zoom out loads, then you see, oh, look, it was non-zero. It was just another root that was out at 1,000 or something. -1,000. Good.
Yeah. Exactly. And so that's really interesting. Like, how do we analyze this kind of system if we have roots that are going out to infinity as we make something small? Let's look back at the slides.
Sure. The minimum point keeps decreasing, says someone in chat, which is true.
Yeah.
The minimum's going down as well. You can differentiate this to get a different polynomial where the roots of that derivative tell you about the location of the turning point. You can do that, and I recommend it. Is this the algebra? Yes, this is some algebra.
Yes. So let's try and actually analyze that. So we know that we have one root that stays near x equals 1. And that makes sense because if we make epsilon equal to 0 and we just have our linear equation x minus 1 equals 0, that obviously has the root x equals 1. So that's what we're expecting our like linear kind of solution to be. It should move towards x equals 1. And then we saw that this other root goes to negative infinity. It's going to get really, really big as epsilon goes to 0. So let's try the same method we used before. So we're going to sub in a power series, like a series where it's different powers of epsilon, which in shorthand is called a power series. So exactly the same series we had before, but now in this new equation. And if we do this and we do all the algebra, I won't take you through it in detail, but we're doing the same thing before, subbing in, solving equal to 0. We get only one solution this time. We get this 1 minus epsilon plus 2 epsilon squared. And we are expecting 2 solutions because it's a quadratic. So the interesting thing here is that in our first one, we had that choice that James was talking about where we had like the 2 different paths, we got 2 values for A. Here, we're only going to find 1 value for A if we use this method. I'd be interested to know if the chat has any guesses for why this series, this form of the series where we're taking powers of epsilon, can't possibly represent something going to infinity.
Right, so if it really is true that the root is going to minus infinity, then you can't write it in a series like this for some reason. It's like incompatible somehow.
Yeah,
okay.
Because we know that the behavior has to be that x becomes really big in magnitude and negative, so negative infinity, when epsilon gets small. But if we think about, if I'm just subbing in a small number for epsilon into this series, I'm going to get A plus something really tiny plus something even tinier, because a small number raised to a power becomes smaller. And so I'm just adding lots and lots and lots of tinier things. And I need my solution to get like really, really big. So that's kind of fundamentally the wrong approach to get something really big.
There's a
Yeah,
fix.
I saw someone say it's like a decimal powered in the chat.
Yeah,
Exactly that.
it's yes. There's a fix. We've got about 10 minutes on the clock, so I'm
Yeah.
thinking, should we skip a slide and show them the fix, the way that you can do some maths about minus infinity, even though you're not allowed to put minus infinity as a
Yeah,
number
I
in your
think these
calculations.
last three slides will like see us through, is my
Okay.
guess.
Okay, cool. Right. Well, let's do them at normal speed then.
Yes.
Okay.
So if we go to our next slide, this is where we start looking at how can we fix that? How can we work with this thing that goes to negative infinity instead? So we want a series still, like a kind of core part of this theory that depends on like under the hood stuff, is that we need our series to be in the form of epsilon raised to a power. So if you could just hit enter twice again. We need still constant epsilon power working through. But if we were confined to that format, what could we raise epsilon by? Like what exponent could we put on our epsilon so that the result gets big when epsilon is a small number?
There's a question in the chat that says, how do we know the coefficients remain bounded? Which I think sounds really clever, but of course the coefficients are just numbers. They can't hurt us. They don't depend on epsilon. We're trying to guess a different function, a different power of epsilon, which we can decorate with a numerical coefficient, but a different function of epsilon that can get really big, that is unbounded. So far, we've only considered things like a constant, a number times epsilon, and these things are tiny or constant sized when
Yeah.
epsilon is small. Yeah, so there's some suggestions in chat like negative numbers and an anonymous person. So we have negative, negative, negative with a question mark, -1, no punctuation. Chat uses question marks to try and hedge on the
Yeah.
more question marks, the more hedged.
Yeah, that all sounds
Negative.
a great idea to me. A negative power is indeed what we're looking for. So if we jump to the next slide, we can see that if we did epsilon to the power of -1, which was a great suggestion, then as epsilon gets small, so as we move to the left on this graph, 1 over epsilon is going to get really, really, really big. Of course, that's undefined when epsilon is equal to 0, because we're not allowed to divide by 0. But it is defined for any positive value of epsilon.
That's the sort of behavior we want, isn't it? This behavior that when epsilon gets really small, something, 1 over epsilon, I think gets enormous.
Exactly. And people who suggested like other negative powers, like -2, -3, those also can work. They're just not what we need for this particular problem. But there are some problems where you might need a 1 on epsilon squared or something like that.
Yeah, I'll put a note in the further reading, but you can do a kind of comparison of the terms to work out how fast this thing's diverging, how fast it's growing as epsilon goes to 0.
We are potentially going to discuss that, but we won't have time.
Oh, sorry. Okay.
But that's all good. But yeah, so the final thing we note is that let's try and sub in a new series instead. So we'll do x equals a on epsilon. So that's that 1 on epsilon term that's going to blow up to infinity. And we're hoping a here will be a negative number so that it will go to negative infinity. And then we have the rest of our terms that we had before. So we still have like additional corrections that will tell us kind of about the speed a little bit, but the core fact is it's going to get really, really big quickly because we have this a on epsilon out the front.
Yeah, I'm trying to plug it in to see what happens. I think we're going to see in a second, aren't we? If you put it in here, then you'll get something like a squared over epsilon squared times epsilon. If you put it in here, you'll just get a over epsilon. So if you want this to be 0,
yeah,
then you're going to need, right, okay, yeah, sorry.
So if we substitute that in, I'll just give you the cheat of the answer and you can spend some time yourself trying to work that out. It is the exact same process as what we did before, where you just sub it in, expand, ignore all the terms with an epsilon cubed or higher, and then solve equal to 0 at each step. But you'd have to start by considering first equations that have a factor of 1 on epsilon to begin with.
Okay. I've got this -1 solution.
Yeah.
I've also got this 0 solution. What's going on there?
That's actually a really good point. James, if you sub in a equals 0, what does your series look like?
Oh, if I put 0 here, if I kill this term, then I get back to constant plus epsilon times a number, the stuff that we had before.
Exactly. And yeah, so if you use a equals 0, you will get the result we got on the previous slide for the other group.
Oh, right. We've just expanded the range of our epsilon powers. So a equals 0 kind of reduces us back to the calculation we were doing before. Right, good. That's why I've got two solutions. And then this one.
Yeah, so we were hoping we would have a method that gave us kind of 2 solutions originally, and we didn't. But if we had started with this one, we would have gotten 2 solutions that we expected. And yeah, so we find that.
Thank you.
So we find that a equals -1 gets us to this -1 on epsilon, and then we find b equals -1, c equals 1, moving on, and we get this kind of series. So the last thing I want us to do is just see that this actually does work. So if we go to our Desmos again, last one, so example 4.
Yep, I can do this. I think this is 4. Yeah, is it gonna work? Yes. Okay, in it goes.
What I have here is we have the equation, and we have the, you can just make epsilon kind of bigger for a second so that we have a smaller thing to look at. We have in red our first solution that we figured out with our standard series. So just the a plus bx plus cx squared. Oh, I'm sorry, a plus b epsilon plus b c epsilon squared. So that's that solution, and we're plotting that as a vertical line. And then in blue, we have this one for the root going out to -infinity that we've just calculated. And hopefully you can believe that these roots are aligning pretty well with where this quadratic is crossing the x-axis. And then we can see that as we make epsilon smaller, they actually become an even better agreement in theory. And yeah, you do a little test, zoom in and tell us how good it actually is.
Pretty good. So the actual root, I still haven't found the difference here. So this is not using the quadratic formula. This is just plug and play, guess a format for the answer and try and substitute. And yeah, I've zoomed in and the actual root looks like it's about -125.99213, whereas this blue line is at -125.992, which is pretty good.
Yeah, it's for just solving like the very basic quadratics, not having to take a square root at any point. Not even really quadratics because you're subbing in a variable at each level, so they're linear equations you're solving actually. You get a really good close answer to this really big root where the algebra would be kind of annoying if you're trying to do it by hand with like an explicit value of epsilon.
So the thing's going to -infinity, but amazingly, you can still do maths on it anyway. You can still predict where is it as epsilon goes to 0. You can do these really precise calculations just by doing a little bit of algebra. I've almost zoomed out far enough that it looks like a quadratic again. Oh, there we go. Lovely.
Yeah. Beautiful. That, we might just jump to the very last slide for a second. So I'll tell you a bit about how this all relates to kind of like the real world a little bit. I had lots of extra content that's juicy, so there'll be good notes that you can go through after. But yeah, so I use this kind of math in everything I do in my PhD and also that I did in my master's. So the core concept, like I said before, is, am I frozen? No, I'm good. The core concept, like I said before, is that you're solving a simple problem that you know how to use, and then you're using series. So we're subbing in series into our formulas to get simpler equations we can solve for a more complicated problem. So simple thing, sub in a series, more complicated answer. And for examples of that, in my master's work, I was looking at forces on particles that were close to the shape of a sphere, but weren't exactly a sphere, as they moved through a water or like a liquid. And to do that, I would solve the equations for particles that were spherical, which are nice and easy because they have lots of symmetry, and then do some like corrections to make them non-spherical. And then what I'm doing in my current PhD work is related to this concept called boundary layers, which is where we're solving equations that have really, really steep sections. So if you look at like this little plot, for example, you can see that in the middle, it's very flat, but on the left and right, there are very steep gradients. And that makes the equations that govern the system really difficult to solve. But we can sub in series into the governing equations in those little bits and solve the steep sections by themselves. And using these kind of series techniques, that's a broader concept called asymptotic series. And that allows you to get bigger ideas. And then the third image I have here is a kind of cool thing that this math of like asymptotic series was kind of developed. So this is representing an airplane wing. And this whole area of math, as far as I'm aware, this could be hearsay, it was kind of developed because people couldn't figure out how planes could fly. Like if you do the fluid mechanics of planes and the forces on the plane wings, it shouldn't work. They shouldn't fly. And they realized that they were kind of missing a bit of the maths in the model, and that was these really steep gradients appearing in just a small level outside of the plane wing, and they need to use these kind of boundary layer methods or perturbation theory methods in order to actually solve for the air velocity outside the wing in that really tiny region. And that provides the force that can allow a plane to fly. So yeah, this kind of area of math was motivated by like real world observations that we couldn't explain, which is kind of cool.
There's a small parameter, there's a small epsilon for the stickiness of the air, and if you just set that to 0, then you can't understand flow around aerofoils. So yeah, right, good. Okay, links for the further reading, I am sure. Final bit of advice for EPQs: if you need a topic, then you could look at the Maths Club website, which you can find at maths.ox.ac.uk/r/club. We've got about 100 past episodes. Click on something that sounds interesting, click on the further reading, maybe find out a new favourite source of maths over there. It also says down there that we're supported by the University of Oxford and by Jane Street. The University of Oxford is the university where we work. They employ me and this computer, who's done a very good job. Good job, computer. And we're also supported by Jane Street. Jane Street are a trading company. You can find out more about them at the bottom of the Maths Club page. They do puzzles, they employ mathsy sort of people. And if you're interested, you can find out more about them through their events and even summer schools. Good. Right, Chance of Getting to Promise Europe. I think they have a lot of applications, but it's merit-based, so if you have done their problems and had a go at their maths, you can have a go at that. This is very rude, I'm just talking to chat now. Hi, Georgina. Anything else you want to plug at the end, or other things we should look at?
No, I don't think so.
Okay.
Yeah.
I think we'll wrap up here. Thank you so much for coming on the show and telling us about your research and telling us about perturbation theory. Lots for them to try at home and lots for them to see in further reading notes, which I've really got to write tomorrow. All the best with the rest of your PhD, and maybe we'll see you again. At the end of the episode, we always say we will see you for another episode in 167 hours. We'll see you back here, same time, same place, for the Oxford Online Maths Club. But until then, have a nice evening, have a nice weekend, take care, and enjoy your maths. Bye, everyone. Good night.
Yeah.
Good night. It's like 6 o'clock. I've never nailed the sign off. 100 episodes and I still don't quite. Bye everyone.